Hello everyone. In this video, I'll be talking about this paper titled Datasets for Deep Data Driven Reinforcement Learning. The authors are Justin Fu, Avril Kumar, Ofrin Asham, George Tucker, and Sergey Levin. So, as you can see, the title, we can decode some stuff here like data driven, like deep data driven, suggests it has something to do with large data set. Yes. So yeah, so it introduces something called offline reinforcement learning. uh, it is also called as batch RL. So traditionally online RL can be depicted as follows. You have a data block, or you can call it as experience replay or something else, and there is your algorithm, RL algorithm block, and you have access to a simulator or access to the environment directly. So this is the block. So all of these blocks communicate with each other, and this data block is updated using the simulator data, and then the objective of an RL algorithm is to output a optimal policy pi star. Now this offline RL, what it does is it doesn't have access to the simulator, so it just has data and the RL algorithm, and you have to use the data to come up with the uh, good enough policy. So this is what the abstract says here, and it says more, which I'll go into more details now. So this paper actually, what it focuses on is to design a benchmark, a data set which is tailored to this offline RL problem. Since the online RL has the simulator or the environment interactions happening, and offline RL has just access to the bunch of large data set, you have to have a good enough uh, data set on each of the benchmark tasks and to actually evaluate your offline RL algorithm. So yeah, and additionally, this is where you want to start. This paper is where you want to start exploring on batch RL if you are researching on this problem. So yeah, so here the authors start outlining the key properties required for the data, which are very which makes sense for offline RL to work. So the properties which they come up with is data sets generated by humans, and the like multitask data sets. You don't have to have a task oriented data sets, but a multitask oriented data sets is what you are looking at. And data sets can come from some suboptimal trajectories as well, suboptimal policies as well. So yeah, we'll go more into details as we go further. So this is what the abstract says right now. Then we'll focus on research effort methods on try that drive substantial improvements, not just on simulated benchmarks. So yeah, the and since, for example, an application would be a traffic management system, like you have bunch of data sets from ages, so that would be one of the this would be one of the application where offline RL would work pretty well. So yeah, going into the introduction now. And one more thing about this one more observation about this abstract is that these data sets are not suggest that policies are not just history dependent policies, so they can be non-Markovian as well. So it's a richer class of policies which you need to optimize over policies. So the introduction. RL is an inherently active learning framework. As you know, RL until now it has been focused on interactive learning kind of a domain. So extending those state-of-the-art results will be a problem for won't be directly extendable, so you need to develop new methodologies here. So but people in supervised learning have studied a lot of large fixed data sets, coming up with good objective oriented policies and stuff like that. So yeah, I think here's a picture. So you have large data, supervised learning. Research on supervised learning has improved a lot. So you have to bridge the gap, or bridge this and the online RL, so that you would get good offline RL methodologies. Yeah, I might have messed up this spelling, so yeah, sorry for that. Yeah, now deep neural networks can enable. So this is talking about the supervised learning, how it improves on just using the data sets. So yes, and these are the applications which I mentioned, like operational research, healthcare, which have a lot of already gathered data. Like another simple example would be power systems, where you have data of energy consumption and stuff like that over couple of hundreds of years. So yeah, you have lots of data. So this is an interesting formulation. Yeah, so here we go further into the introduction. Here there is a mention of how offline RL setting addresses major limitations. Yeah, major limitations of standard. Okay, so first, by maximally leveraging offline data, uh, yeah, RL algorithms can substantially lower the sample complexity. Yes, I mean, this would be a point one. So if you use the large data set available, uh, let's say you have come up with some offline RL algorithm and it outputs some pi tilde star, which is optimal in the sense of this data. So you can deploy this pi tilde star to an online RL which actually interacts with the environment sim, and then this would yeah, this is just a heuristic, but yeah, this would probably reduce the sample complexity. I mean, the number of samples it require the online RL requires might be reduced. So this is what this is saying, this paragraph is saying. Now there is something else here, so yeah, let's go to the second point. Offline RL setting elevates many of the safety concerns. Yeah, this is like the most important part of the online RL, which is a safety concern. So right now, offline RL will remove the safety requirements during the training stage. Online RL suffers from safety. This is lifted from offline RL. So yeah, this is good. Now the last one, the offline RL setting allows policies to be pre-trained on such that they may yeah, so this actually goes back to the point one. So yeah, now the third one is more so you might have heard about exploration and exploitation, pair and balance required in RL, required in online RL. So right now, since we are just focusing on the data set, we don't need to focus on exploration. Just data exploration is removed. So yeah, that is why it kind of decouples dynamic programming and the optimization with the exploration aspect. So yeah, offline RL provides some advantages over online RL as well. So yeah, let's see. This one says most recent works in this area used data collected from fully or partially training runs on standard. Okay, so yeah, as I said earlier, here we are introducing non-Marco policies as well. So this is kind of hindering the richness of the data set. So yeah. Now, in fact, it also says that in fact it is not even clear whether this setting permits much improvement over the best average policy collecting. Yeah, we need some theoretical guarantees to say this for sure, but yeah, right now it doesn't make sense. In this work, let's see, in this work our aim is to, okay, yeah, this is what the abstract said. So yeah, we have to like create a good amount of data sets for good amount of benchmarks, tasks, so that offline RL can be compared. Yeah. So now going into more details. Yeah, here again a suite of tasks and data sets are provided. We focus on dataset compositions that might reflect realistic settings. Okay, yeah, I mean data from the human demonstrations, from previous tasks, no, not tasks. I mean, not task oriented. So yeah, and data from non-learned scripted controllers. Yeah, I mean suboptimal controllers. Different keywords. So yeah, we hope that our evaluation provides insight into existing shortcomings. Yes. So hopefully, yeah, that's why I said that this is the first paper people need to go through before starting to develop the offline RL algorithms. Now, moving into the background, this paragraph mentions the MDP formulation. MDP defined as this tuple where S is the states, actions is A, P is the transition probability matrix, R is the reward structure, rho naught is the initial distribution used, and the gamma is the normal discount factor. The goal in RL is usually to find a policy which maximizes this average cumulative discounted reward JPI, the usual definitions, and then the so-called off policy algorithm. This comes under the online RL as under the name off policy RL. There is one more thing called on policy RL. Yeah. So off policy is still using the data, which is experience replay. However, off policy methods updates its buffer by using the latest policy. So this is not exactly the offline RL setting, but yeah. So here they mention that Kumar et al. 2019 paper says that the state of the art of policy RL can't be directly extendable to offline RL setting. So yeah, this is one thing which mentions here. As to supervised learning, optimal supervision at the state is not provided. yeah, I mean, only suboptimal actions are provided, so this is acceptable. The algorithms needs to implicitly perform complex, yes. So the similar result like Kumar et al. Even Saranberto 2018 shows that off policy RL can't be directly extendable to offline setting. Just to add something in this background, mm, yeah, if we take this maximization of j pi, max of j pi, the current theory says the current theory says in the space of history dependent policies, the optimal policy is by star. So now, but in what we require here is much richer class, which are non-Markovian, plus these things, plus other general human-centric data, policies. So yeah, right now this is a richer class, so we don't know if the optimal policy lies here or here. So this is an open question. So open Q is pi star the same as, let's rename this pi star by tilde star, yeah. So is pi star is equal to pi tilde star? If not, what is it? Yeah, basically we need to come up with new methodologies to prove this stuff. And yeah, this is an interesting observation made here. So yeah, moving further in this paper, the third section is titled Task Design Factors. Here basically they mention the properties which I promised earlier. Let's see the properties of the data sets which the offline RL is looking at. So yeah, firstly what they mention is offline RL algorithms must be able to handle extensive distribution shift. Let's see what is the distribution shift. So let's consider rho SA as a measure of state action pair visitation frequency. The challenge which they are talking about here is to quantify rho SA, which the offline policy corresponds to, and difference of these things. the visitation frequency coming from the dataset policy, or which they call as behavior policy, a generic term to encapsulate all these different properties. One thing to note that in on policy RL, this distribution shift problem doesn't occur, since we are actually concentrating on the updated policy to generate the data itself. So the hope in on policy RL is that as we update the policies and k tends to infinity, or is just sufficiently large, then we don't need to worry about the distribution shift, is what the current theory says. So now going into the properties here for the dataset generation. First one is called undirected and multitask data. So you don't know what's the objective of the data is. Here is a simple figure which they provide as an example. So let's consider path A, the blue one. You don't know if A is this the source, or is this the destination, or some other different objective, like minimizing the routing problem, or there are many number of tasks here which can fit this figure. So the objective, the offline RL can output the path C, combining A and B, seeing that both A and B are reaching the same points here. So it can just combine the first half of A and the second half of B and just output C. This is a simple example for the undirectedness and the multitask in the dataset. So now the next one is suboptimal agents. Yes, this one should be clear that whatever dataset that has been generated may not be actually coming from the optimal RL agents every time. So you need to have control on what to infer from these suboptimal agents as well. So here they mention that offline RL can still potentially learn optimal policies from suboptimal data, but require rewards to be specified in order to provide learning signal for the algorithm. We also know that this type of data is currently predominant method for benchmarking offline RL. So here they mention imitation learning, which always uses the expert data or optimal data. So optimal agents. So the third type of dataset which the paper looks at is data generated from non-RL policies. like human generated policies or some kind of heuristics dependent on the problem itself. So human dependent with external cues of the data set. So yeah, these are non-Markovian as I said earlier. So offline RL algorithms, so the objective is to learn efficiently when under the yes. So the final type of data set is called as narrow data distributions. These are actually just contrast of S, which is the expert policies. So yeah, if the behavior policy which I mentioned here consists of behavior policy encapsulates belongs to by USPN or this circle can now be clearly said is equal to USPN. So yeah, this clearly defines the problem. Yeah, narrow data sets as when utilizing human demonstrations for handcrafted policies. These are expected to be optimal because the autonomous driving is, I mean, you can't expect some suboptimal policies being deployed in autonomous driving. So you can think of these things as expert data set. Yeah. Now here finally they mention that for the task to be diverse, they include both locomotion and manipulation robotic tasks. So yeah, and robotic locomotion tasks are gathered by OpenAI Gym tasks. So yeah, this ends the description of properties. Now moving on to the fourth section, which is titled tasks and datasets. Which basically wants to use all these properties and come up with good data for the tasks. So yeah, so now moving on. The subsection is titled diagnostic tasks. So debugging and prototyping algorithms. So kind of a sanity check datasets for offline RL algorithms. Yeah, Maze 2D, as the name suggests. There are different paths here. For example, let's consider the data set as the paths. Yeah, 1 to 2, which is green, and the next one is in hello, which is 2 to 3. This is yellow, and then yeah, let's say the offline algorithm, when asked for the routing from 1 to 3, it actually gives combines these two paths and optimally gives the um, path in this way. Like it traverses like this, it never goes to 2, but yeah, it just jumps here. So this would be an ideal situation. I mean, this is what you can expect from the offline RL algorithm. So yeah, this is what is mentioned here. So now yeah, there is another task, mini grid. So here yeah, there are 4 rooms with short openings between them to traverse between the rooms. So the data set in one environment is collected from planner, which navigates between the randomly selected goal locations, and another task mentions collects data via random actions. So yeah, these two provide some sanity checks for offline RL algorithm. Now moving on to the actual benchmark tasks, which are expected to be some complex tasks and larger data set to actually support the earlier sections. So now the first task is Jimojoko, which consists of like these 3 tasks, the locomotion tasks. So the first data set consists of data generated by suboptimal policies. Like for example, just train the standard RL algorithm SAC only for a few steps and then stop and then collect the data. The next data set is coming from mixing varying amounts of expert demonstrations and suboptimal data. So yeah, the suboptimal data and the experts are mixed in these things. And the final type of data set is collected by all as the samples observed during the training. Yeah, this seems to be the expert data, like after it converges to something or after it reaches some desired level of rewarded return. So yeah, yeah, the next environment is Ant maze. It's like maze 2D, but now you have to control the ants joints as well. That adds to the complexity of the problem. So here the data set is similar to the previous ones. Like here a narrow data set is generated, which is the expert things, specific goal for the specific start location, undirected. So yeah, a diverse data set commanding the ant to go from randomly sampled goal to reach the randomly sampled goal from randomly sampled start location. So this is also an undirected version. So now the ant is commanded specific hand-picked location in the maze. So there is no optimism coming into picture. Like, you are not trying to traverse between two different locations optimally, but yeah, you have to like reach some locations. So this is like that set U, which I mentioned earlier. So yeah, this looks like good data set. The narrow behaviors cannot be represented by Markovian policies. Like, yeah, human behaviors. The last environment is called Adroit. Here, if you can see a picture, yeah, it's a single-handed robot which has multiple tasks here, which is controlling a pen, which is trying to open the handle, turn the handle on the door, or it's handling some hammer kind of a thing. Yeah, this encapsulates the multitask environment. So yeah, here a small amount of demonstration data from humans and large amount of expert data, okay, coming from the SOTA RL policy. So, and they also mixed the data 50-50 of demonstration and the expert policies, call it as cloned. So they say that the demonstration data is realistic, collected from motion capture system. Each task is difficult to solve. The standard, yes, exploration challenges, which make cloning and online RL alone insufficient. Yeah. This is quite a well explored paper. So yeah, now going on to this subsection. Now going into the evaluation section. So yeah, it's just what factors a parameter which actually evaluates the which helps in comparing different RL algorithms. So this is a normalized score. They mention something here like normalized score 0 corresponds to the random agents, and the perfect score 100 is corresponding to an expert. And there is a typo here, and then yeah, they also mentioned that maze 2D and maze performance of hand design controller, yeah, expert data is having the score of 100. For Android, the expert data is coming from the behavioral cloning on human demonstrations. Yes, for Mujoko, soft actor critic is the one which is expert. So yeah, with this we move on to the final section, or sorry, final to the last section. So here they benchmark the prior RL algorithms using the currently developed data sets. So for baseline algorithms, SAC is used, Bootstrapping error accumulation reduction is used. Buck, bear and brack. Actor critic with support constraint on the policy. Yeah, these are the three offline RL algorithms which are being compared here. So they also report results of the pure behavioral cloning, pure SAC, yes. Yeah, this table is summarizing for what domain, what are the different types of data sets they're using. This is the undirected version, the mixed version. Yeah, so as you can see, the number of samples are pretty high, large data sets. This is a weird number. Maybe by coding it was like they ran from 0 through 100, collecting 1000 data points in each loop. So yeah, and yeah, these are the properties which correspond to these names. So yeah, for Android and Mojoko, I think the undirected data sets doesn't appear because these don't have, I mean these have Mojoko setup might have the, I mean it's worth exploring adding you here because they are starting at some random points. Like the rest position, and then they have to get up and then move. So yeah, there is much improvement in these data sets which can be made. So yeah. So now these paragraphs actually are describing the performance in this table. So I tried to summarize it. So in each row you can actually mark the maximum score like this. This one. So these are the online RL and these are the offline RL algorithms. So somehow offline RL algorithm, let me just mark this down, these things, 127, yeah. Gem environments, yes, it's offline RL are performing really good here. So maybe the undirected data sets which exists here are very poor for offline RL. So offline RL algorithms are performing poorly for undirected data sets. So yeah, as you can see for Android, so as you can see Bear is performing better for Android. So yeah. So now moving back to those paragraphs to see if we have missed something else. Let's see. Yeah, there are few exceptions such as environments where exploration challenges make it difficult for. So yeah, offline RL may have advantages. So that is why Bear was performing better, I guess. So now in these scenarios where data is generated via some previously trained policies, yeah. So undirectedness helps into picture here. Gracefully handle varying qualities of single policy datasets and match or exceed. Yes. So the scores were like similar here, these things. So yeah, makes sense. However, datasets generated by mixture policies such as these things can be less challenging. Yeah, okay. So there are places where offline RL can improve much better using these data sets. So the tasks with undirected data property, yeah, are challenging with existing methods, as we saw here. Yeah, these are going negative, so yeah, this kind of is more. So we hypothesize that in continuous spaces, the evaluator algorithms still find it difficult to combine with different pieces of trajectories from the dataset in order to assemble a successful show. Yeah, okay. Yeah. Yeah, we know what kind of things to be addressed from these things to come up with good offline RL algorithm. Should perform better in these scenarios. So here we move on to the section called related work, previous work. So RLR focus in this work is primarily to use offline RL as means to scale RL. So it's like reinforcing RL, online RL itself by the results of offline RL. So yeah, significant efforts have been made to incorporate large dataset of policy RL, but these works generally use large numbers of robots to collect online interaction during training. So yeah. So finally moving on to the last section, we have proposed The authors propose, benchmark for offline RL, data generated by previously. Optimized RL has been used for dataset generation, so can give misleading sense of progress. Particular okay. Yeah, so undirected data should be deciding factor for upcoming offline RL algorithms, which fit many. This is the most important thing. Yeah, we'd like to see offline move from simulated domains to So basically, there should be a strict difference between off policy RL and offline RL. So finally, to say that we hope that providing benchmark but still cheaply evaluated simulation will greatly accelerate progress in the field and create new opportunities. Yes. So with this, I end this video. Hopefully you have liked this video.